Writing an equation from lab data. We're looking at an accelerating object, and we have a distance versus time graph, and a velocity versus time graph. We've accelerated marble down the ramp, used our high-speed cameras, used a video analysis software program called Tracker, and you've collected a lot of data, and you've taken that data and put it into graphical analysis. We've created a distance versus time graph, also called a position time or PT graph, and a velocity versus time graph, also called a VT graph. And you think you're done, but you're not. In reality, you must now analyze the data. You must determine the algebraic relationship between distance and time for your lab. You must determine the algebraic relationship between velocity and time for your lab. You must relate these relationships to the acceleration formulas learned in class. And finally, you have to determine some error using statistics. We have the equations we learned in class. We have the equation for percent difference. We're going to start with the velocity time graph. It's the easiest graph to start with because it is linear. We've done that best fit line, and taking a look at it enlarged, graphical analysis has already done some work for you. They've already expressed the line in the standard mathematical formula where V equals mt plus b. Notice it does not use a y, it uses v, because v is what is on our y-axis. It does not use an x, it uses t, because t is what's on our x-axis. So v, which represents velocity, and t, which represents time, are our variables. Rewriting that equation, we have v, which is a variable on the y-axis, and t, which is a variable on the x-axis, and then multiplying by t is our slope, which is a number. Adding to t is our y-intercept, which is a number. We can get that slope from up here. It's 2.750 meters per second per second. In my labs, unless I tell you otherwise, I always want you rounding to two places to the right of the decimal. So we've got 2.75, and if it's a number, you have to put units with it. So that's meters per second squared. For our y-intercept, if we round that to two places, we get 0.14, and it's a number, so we have to have units, meters per second. That's it. We've written the algebraic relationship for our lab for our velocity time graph. Now we have to compare it to the equations from class. So down below in the left-hand corner, we have the general equations. Which one does this most closely represent? Well, it starts with a v equals. This one has a v equals. This one has a d equals. This one has a vf squared equals. So it looks like it's this guy. So I'm going to write that down here. We have vf equals vi plus at. Well, already we've got a difference here. We've got the t term and the end. So I'm going to rearrange my written equation so it agrees with that. So I'm going to put v equals 0.14 meters per second plus 2.75 meters per second squared times t. So now I've got it in the same order that the other one is. And if we look at this, we can see that the number multiplying t is our acceleration, and the number by itself is our initial velocity. So that means from this equation, this v here is our final velocity. This term here is our initial velocity, and this term here is our acceleration. So we did all the writing the equation and relating the equation to formulas learned in class for our linear graph. Now we're going to go to that tricky curve graph. This is our distance versus time graph, which is frequently called a position time graph. Put the data in, and we've done a curve fit. We've got a quadratic equation there. We're going to look at the data for that quadratic equation a little bit closer. We've got this general form given to us by graphical analysis. So I'm going to rewrite that. We've got some d, which is our variable on the y-axis. So it's not y, it's d, because that's what specifically is on our y-axis. And it's got some number, a, times t squared.
Found something.
Then our second term, we've got some number, b, times t. And then for our final term, we just have some number. So now we have to fill in those numbers. So again, graphical analysis gave us a number for a. It's 1.40. This plus or minus is just telling us the accuracy of that number from the data. So it could be 1.407609, or it could be 1.39231, or it could be anywhere in between those two numbers. We're not going to worry about that right now. In fact, we're not going to worry about that at all in this course. So those pluses and minuses are just telling us how accurate the statistics that graphical analysis does tells us those numbers are. So we're just going to use the 1.40. We're going to round it to 2 decimal places. For B, we've got 0.1348, which rounds to 0.13. And for C, we have 0. At least it rounds to 0. So that's fine. But notice with the curve fit, it does not tell us what the units are. So we have to do some unit analysis here. So in our lab, for this particular set of data, we used meters to measure distance. That means the first unit is going to have to equal meters. So we're going to have some units times time squared. Well, in our lab, we use seconds. So we've got seconds squared. So what unit do we multiply by seconds squared to get meters? Well, we'd put seconds squared on the bottom, and we'd have to put meters on the top. And these would cancel out, and that would leave us with meters. That means the label, or the unit for that number, must be meters per second squared. Looking at the next one, again, we want to end up with meters. And so what unit are we going to multiply times time? Well, time, the units in our lab were seconds. So we would put seconds on the bottom to get rid of it, and we would put meters on the top. So that means the unit, our label for this number, is meters per second. And finally, the 0. Normally I wouldn't look at 0 units, but we will right here. So we want to end up with meters, and we're not multiplying it by anything, so that must mean that just must be equal meters. Okay? So now we've got our labels, our units done, and we've got our equation written. Now we have to compare it to the equations that we learned in class. So we're starting out with a D equals. Here we have a V equals, here we have a D equals, here we have a V squared equaled. Well, it looks like equation number 2 is the one that it's going to be very close to. So I'm going to rewrite equation number 2 down below. Now I'm going to rewrite my equation from the lab, and I'm going to rearrange the terms so they're in the same order. So I'm going to put a D equals, and I'm going to put my term that has no t in it. So that would be this term here first. So it's going to be 0 meters. Plus, I'm going to put my term that has just 1 t in it. So that'd be this term here next. So that'd be 0.13 meters per second times t. Plus, I'm going to put my term that has just a t squared in it next. So that would be 1.4 meters per second squared times t squared. So now we've got it rearranged, and it looks pretty obvious now that this d is our df, that this 0 meters is our di, that this 0.13 meters per second is our initial velocity. And then we got this term here. This is kind of tricky because this must be equal to 1/2 at squared. So I have to do some little side calculations here. 1/2 A is equal to 1.4. Therefore, A must be equal to 2.8. So I'm going to rewrite this particular term as plus 1/2 2.8 meters per second squared times t squared. And then this is my final version. The df equals 0 meters plus 0.13 meters per second t plus 1/2 2.8 meters per second squared t squared. Now I can see that this 0.13 is my initial velocity from this graph. My 2.8 meters per second squared is the acceleration from this graph. And now I can compare my numbers between the two graphs and do some statistics. So from my linear velocity time graph, I have VF equals 0.14 meters per second plus 2.75 meters per second squared times t, which looks like that format. That means that VI is 0.14 meters per second, A is 2.75 meters per second squared. For my curved distance time graph, called a PT graph, I get that DF equals 0 plus 0.13 meters per second t plus 1/2 2.8 meters per second squared times t squared. So my VI is 0.13 meters per second. My acceleration is 2.8. So for VI, the percent difference is the absolute value of 0.14 minus 0.13 divided by 1/2 0.14 plus 0.13 times 100, or 7.4%. For acceleration, the percent difference is absolute value of 2.75 minus 2.8 divided by 1/2 2.75 plus 2.8 times 100, or 1.8%. And now I'm done with my analysis and the lab. Thank you very much for your time.